Welcome to queenon7.com. Please like, share and subscribe my video. Today we're going to learn about Arrhenius equation. Arrhenius actually developed a relationship where you can actually use to calculate the rate of reaction. You probably are aware at the start of the chapter where you actually use the concept of concentration, where you have rate is equal to rate constant along with the concentration of the reactants and raised to the power with the order. So if you these are the order based on the concentration of that particular reactant. So if you increase the concentration of B and it doesn't have any effect on the rate of reaction, it is zero order. If you double the concentration and it doubles the rate of reaction, then that means that is first order, and it will if you actually do that, you carry on with it like second order and third order. So that these powers are actually 0, 1, 2, 3 based on what is the order of the reaction based on each concentration. This relationship you have done at the start of the this chapter. So today we're going to look at how Arrhenius actually used his equation to explain the rate of reaction. Now, why it is necessary that Arrhenius actually thought of developing another equation, and the reason behind it, this relationship only tells you the effect of concentration on the rate of reaction. It doesn't tell you exactly that what will be the effect of temperature and catalyst. You do know that there are some other factors apart from concentration which can actually increase or decrease the rate of reaction. So Arrhenius developed an equation where you can use that to develop the rate of reaction. Now, when you look at the rate, which is obviously is given by K into A into B, he said that rate constant, which is obviously K, and he said rate constant will be equal to Arrhenius constant. Then he used an mathematical exponential E, and then he developed this relationship EA over RT. And I'm going to explain them one by one in this video and an example, and then the next video I will actually explain how you plot the graph and you could use the Arrhenius equation to calculate the rate of reaction or the rate constant. Now, because we are actually involving rate constant into this, K is the rate constant, you know that from the previous relationship. Then you have A, which is obviously pre-exponential. This is pre-exponential term. This is mathematical exponential. EA is the activation energy. R is the gas constant. T is the temperature in Kelvin. So most of the stuff you know, but the one you don't know is the mathematical term. If you do not know this exponential term, you can use the calculator. Its value is 2.718 somewhere, but you do not need to worry about that. All you have to do is you use calculator, you put actually click E, and then you put the expression in there. Now, to simplify this, because this is quite complicated, this I'm going to explain all of them one by one, but I'm just going to simplify this by taking the log of both sides. So you take the log of both sides. So log of K is equal to log of Arrhenius constant, or pre-exponential term, we can say that, minus EA over RT. Now, R, which is actually gas constant, it actually comes from P is equal to nRT. In year 12 in AS level, you probably have done the gas constant when you calculate the volume or the pressure using this relationship, so that this R actually came from the from this relationship, and it is actually 8.314. I'm pretty sure about that. And EA, you can calculate EA, or you can calculate the Arrhenius constant, and or you can use K. Now the reason he developed it, because he is looking at what is the effect of catalyst and temperature, which cannot be explained by using the top expression. So the A and K, all of them will they have some sort of explanation. Now in all this equation, they have a meaning. For example, if you talk about A explains the frequency of the collisions. How much molecules are there who are actually produce collisions, or their orientation of the particles. So A will explain that. Now this collision or orientation can be changed by changing the catalyst or by changing the temperature, because if it's concentration, we can use this equation, we don't need to use that. So A is actually, which is Arrhenius constant, is going to explain the effect of catalyst and temperature. Now the other expression, which is E minus EA over RT, that will explain the fraction of molecules which possess equal or excessive energy, you can say activation energy, which possess equal or excessive activation energy, so they can jump the barrier and convert into the product. So this factor which we use here is going to explain how many of the molecules are going to jump the barrier based on how the effect of the catalyst and the temperature. So that's how you're going to use that. I'm just going to use a small example where you can actually use that and explain. Now we're going to use the Arrhenius equation to calculate the activation energy. So you have to actually arrange the whole equation. You do know that the expression, you cannot use that because it's a little bit complicated. So you will convert that into this form by taking the log of both sides. Once you develop that, you look at the question, calculate EA. So you need to sort EA out of this equation. You have been given the temperature into 330. For example, if they have given you a temperature of 25 degrees centigrade, all you have to do is you have to actually add plus 273 and it will be converted into Kelvin. And after that, the rate constant is already given, which is actually K, and then you have been given Arrhenius constant, which is pre-exponential constant, so A will be put in 4.5 times power 13. Then you have a gas constant, which is R is equal to 8.314, and you will be using that. So let's start actually in the calculation. So you have to rearrange this equation. So what if it's log of K is equal to log of A minus EA over RT, I will actually convert that into, I will take the EA over RT onto this side. Because it's minus, according to mathematical rule, it will become plus. So I will take all of, I'm going to do it one by one so everybody can understand it. If you take all of this on this side, so that will be log of K plus EA over RT is equal to log of A. Alright? Now, I would like to convert that into only EA over RT. So this is plus value log of K. I will take this and bring it on the other side of the equal sign. So it will become minus. So that will make it EA over RT is equal to log of A minus log of K. Once it's done, you are going to take RT onto that side. But because this is actually an equation with a subtraction sign in it, RT will be multiplied by both. Because it is actually in the denominator, it will go on the other side on the numerator. So EA is equal to log of A minus log of K, and we put RT there times by that. Now the problem here, when you do the calculation, and this is from my personal experience, when I was doing this with my A-level students, what they did is they tried to use this whole equation, they put the values in the one equation in the calculator, and they came up with the some 33,000 kilojoules per mole of energy. And that is not the exact answer. The problem here is in mathematics, the multiplication will happen first and then the subtraction will happen. So please make sure that you solve this first and then you times by RT, whatever the value is. It is then you will get the right answer. So do everything step by step in the actual exam. So let's start it. So you have EA. So I'm going to start EA. You have log of A. So you have Arrhenius equation, which is 4.5. So which is 4.55 10 to the power 13. Then minus, you have log of k, so you put log of k and the value is 1.30 10 to the power minus 4. And then you will have a r, which is 8.314 and times 330 Kelvin outside. So you can times both of them together and you subtract them together and then you times it by whatever the value is there. The EA will come up as 110, probably 9 or I think 9.9, something like that. I'm not pretty sure exactly, but something like that if I'm not wrong. Yeah, so it's actually 10779.9. And it will be joules because this is energy, joules per mole. Now you always calculate the energy in kilojoules per mole, so you will convert it by dividing by 1000. So that will be actually 111 kilojoules per mole. And this is how you use them. So if the question is like that, you can just use the values, you convert the temperature into Kelvin. That's the first thing. You solve the equation accordingly, separately, and then you will put the values in and you will get the answer. Thank you very much. Wait for the next video about the Arrhenius equation by plotting the graph. Thank you. Now we're going to also look at what is actually happening when you increase the temperature. What will happen to the activation energy or what will happen to the rate constant. So when the rate constant, you can see that actually is there over there. But if you actually look at this simplified form, if the activation energy increases, that means the rate constant will go down, because obviously it's an exponential form. So activation energy, if the barrier will increase, the less product it will make. So because of that, the activation energy should always be lower to achieve more product to increase the rate of reaction. So EA, if it goes up, the rate will go down, right? But if you increase the temperature, the rate will go up, because the more collisions going to happen, and more molecules will have the activation energy, and they can achieve activation energy quickly because they are colliding quickly by the increase of the temperature.